Okay. All right, whoop. Okay, so this is the division. So the planes are divided into things called blocks, and those blocks contain a bunch of pages. So the pages are sometimes the same size as the pages we use for memory, so that 4096. Sometimes they're different size pages, so they don't have to necessarily match memory. They can be like 8 kilobytes, something like that. But they're divided in, the pages live within a block, and that's where the complexities happen. So pages, typically they're 4 kilobytes, and that lines up nicely with the pages we use in memory. But they have a few weird caveats. So reading a page is really, really fast, like on the order of 10 microseconds. Writing to a page takes a lot more effort, so it's like 100 microseconds. And then erasing a block is like 1 millisecond. And you might look at this and be like, well, that's weird. What about just erasing a page? Well, that's where the complexities come in, because you are not allowed to just erase a single page. You have to erase a block. And a block contains multiple pages, so I can only erase blocks, and that would erase multiple pages. So the other silly rules of this is you can only read complete pages, and you can only write to freshly erased pages. So I can't just overwrite data without first erasing it. And again, remember, erasing is done on a per block basis, and usually a block will have like 128 or 256 pages. And again, that means I have to wipe out the entire block before actually doing some writing. And again, writing slow. So we might even need to create a new block if we want to just modify a single page. Well, you know, if we modify a single page, well, there might be 127 valid pages on that block. To modify it, we have to erase the entire block, and we would have to erase those other pages, so we'd have to save them. We'd have to move them to a freshly allocated block, and you can see how this gets challenging. So fortunately, we won't have to deal with the issues. We're just taking a brief overview. So the operating system has to help with this, so the SSDs will garbage collect blocks. So if you're using a block and there's only a few pages left on it, well, what it could do is it could say, well, there's only like 2 pages left, so I may as well move these to a freshly allocated block and then just completely erase this block, so now I can write to it again and I have some more space. So moving those alive pages are going to be some overhead because I'm just copying pages that exist anyways, but I'm doing this because I want to free up that block so I can actually write to it again. So this disk controller is going to be really dumb. It doesn't really know what blocks are still alive and in use by the operating system that are referring to files and things like that. So your operating system is going to have to help the drive and say that, oh, okay, maybe this pages or this whole block I'm not actually using anymore, so you're free to just erase it. You don't need me to do it. So that's what the trim command is, if you've ever seen that. So the trim command, that's an option for SSDs as like an optimization to get much better performance out of it and also increase its longevity. So the trim command, essentially all it does is inform the SSD like an entire block is unused, and then the SSD itself will have a little controller on it, and it's free to erase that entire block without moving anything. So by default, it would have to move things to be safe, but if you're not using anything, you can just erase the entire block. You don't have to worry about it. You don't have any overhead, and the SSD can just do it while it's otherwise idle because it has its own controller. So far, that's about all for hardware. We won't get into too many details. The thing that comes up is, well, a single device, if you are trying to be resilient and protect against a drive failure or something like that, single devices are often a bad idea. So sometimes just having a single hard drive or SSD is called a single large expensive disk, SLED, to kind of make fun of it, because it's essentially just one giant point of failure. most of you in your life have probably had a computer die on them or a hard drive die on them, and then guess what? All your files are lost and you're screwed, right? So you usually don't want that failure, especially if it's really critical data. So for instance, like, I don't know, it's like your PhD thesis or something like that. You probably don't want that to fail because there goes like 3 years of your life or 4 or 5 or however long it takes. So there's another technique called RAID, if you've ever heard of that before. It stands for Redundant Array of Independent Disks, and that aims to use multiple drives together to provide some data loss, so some redundancy. And redundancy is just having multiple copies of the data to prevent data loss in the event that a single drive fails, because that happens all the time. And they can also use this redundancy, having multiple copies of the data, to increase throughput or otherwise go faster than a single disk. So for instance, if you're Google or something like that, you will have tons and tons of disks. And with hard drives, it's not a matter of if it will fail, it is a matter of when a device will fail. So hard drives fail all the time. It's someone's job at like the Google data center or the Amazon data center to just go through and replace bad drives, and that's what they do all day. So there are many techniques to combine two disks. So each cylinder in this diagram represents an entire disk, and then the numbers with the letters represent pieces of data. So RAID 0 is called a stripe volume, which it just distributes that data over the disk. So this file, let's say the file name is A, is in 8 different parts. Well, instead of just having all 8 parts on a single drive, it just splits it across 2 drives. So essentially each drive gets half of the file. So A1 goes on disk 0, A2 goes on disk 1, A3 goes on disk 0, A4 goes on disk 1, and then they each have half of the data on them, right? So any questions about that? Yeah?
If disk 1 with the field, right?
Yeah.
You only have half your data that you can recover.
Yeah, so,
Does that mean,
yeah, so in this point, well, if disk 1 fails, I lost half my file, and I can't recover anything. So this does not help you for failures. It's actually worse, right? So the default case is if my disk drives, my disk dies, I lose everything, right? In this case, if either disk drive dies, I lose everything. I lose half, but half a file is useless. So you still can't reconstruct it or anything. So this is actually worse if you care about the integrity of your data, because now instead of a single point of failure, I now have 2 points of data, or 2 points of failure. So why on earth would I do this? Well, this is primarily for speed. So instead of reading a file from a single drive, I can read a file twice as fast. So I read 1/2 from this drive and 1/2 from that drive. So I use both disks at their full speed, so I get a 2 times speed up, or a speed up of how many disks I actually have. So this is purely for performance. So unlike if you have a sick gaming rig or something like that, it might have 2 drives that are in RAID 0, and the reason for that is to go fast. So the con is, well, you get lots of speed ups, but any disk failure results in data loss. So you actually have more points of failure. So any questions about that? So RAID 0, go fast. The other extreme is something called RAID 1, and that is a complete mirror, and that will mirror all data across all the disks. So say file A is now just in 4 parts. Well, on disk 0, it would have the entire copy, so it would have A1 to A4, and then disk 1 would also have an entire copy, A1 through A4. So now, in this case, if either disk drive dies, then I don't lose any data, right? So if disk 0 dies, doesn't matter because my data is all on disk 1. All right, any questions about that? Yeah?
Do we know that like the memory that we need is like less than the size of one disk? Because if it's longer than usually just like split it over like multiple disks, but if you're duplicating, then you can't do it.
Yeah, so like if each disk, say if each disk was, I don't know, 2 terabytes or something like that, then you could only store 2 terabytes of data in total because it's a copy on every single disk because they all look the same, right? So that's another point to take. Yep.
But do you also get the performance enhancement with RAID 1? I didn't.
Yeah. Yeah, so that's another question. Would you also get the performance enhancement with RAID 1? Or, yeah, RAID 0, right?
With this one, RAID 1,
Yeah.
would you get the performance enhancement as well?
Yeah, so if we were to read a file from this, could we read half from one disk and half from the other disk?
Yeah.
I see a no. Why no?
Like, I don't know if, are we allowed to read from like different sections of disks? Like,
Yeah.
can you read the second half from disk 1 and the first half from like disk 0?
Yeah, you can. So in this case, if you're reading, I could read A1 from disk 0, A2 from disk 1, A3 from disk 0, and A4 from disk 1. So I could get double my read performance if I wanted. But if I had to write data, well, then I have to, if I like make a new file called B, I have to put B on both disks, right? So for writing, I don't get any benefit because I just have to do the same thing for every single disk. So it behaves the exact same as a single one. Yeah.
So like, if you're writing just 2 separate disks, like it's kind of like running in parallel.
Yeah.
So it wouldn't like increase the time.
Yeah, so I can write that entire file in parallel to both disks at the same time, but it's gonna have the same performance as like a single disk, right? I just do it in parallel. So I can speed up my reads in this case because I could read part of the data from each drive, but I can't speed up my writes.
So far, don't you drop out the storage, right?
Yeah, so this one, I waste a lot of space because, well, I can only have a disk of storage. So if each of these disks was 2 terabytes, then I can only use 2 terabytes. If I had a third one here, so with RAID 1, the same rule applies no matter how many disks you have. So I could have another disk that would have the entire copy too. So I could speed up my reads by 3 times, but my writes are still like a single disk, and I can still only use 2 terabytes. While in RAID 0, if both my disks were 2 terabytes, then I can use 4 terabytes. If I had 3 disks and they were all 2 terabytes, then I can use 6 terabytes. So this lets you use all the available storage, but you get speed benefits, but you created more points of failure. Yeah, so with RAID 1, real simple, but kind of wasteful. So it has really good reliability. As long as a single disk remains, since all of them are copies of each other, you have not lost data. So if I have 10 disks and they're all copies of each other, I can lose 9 before I lose my data, right? Nice and safe. And it also has good read performance. So I can split up my read across all the disks, get a nice speed up, but it has a really high cost for redundancy. Everything is just an exact copy of each other. We can actually do a bit better. And the write performance is the same as a single disk. So these are the 2 extremes. So likely you want something that is also a bit fast, that doesn't waste as much storage, and also has less points of failure. So there is something called RAID 4, and you might ask what happened to RAID 2 and 3. 2 and 3 were bad ideas. So we go straight to 4. 4 is also a bad idea, so this one's not actually used. So we'll do a little tweak to this, but RAID 4 is the first one that actually makes some sense. So what RAID 4 does is it essentially takes the idea from RAID 0 and distributes the data across all of the disks. So in this case, I have 4 disks, and I distribute the data across 3 of them. And I'm going to use the last disk here, disk 3, for some parity. What's parity? Parity is just some information I can use to reconstruct the answer in the case that I lose something. So in this case, the parity would be an XOR. So it would be an XOR of all the bits in A1, A2, and A3. And that way, I can reconstruct the information if one of those disks dies. So how would that work? So anyone remember how XOR works? Yeah.
All right, so you have 0, 0, 0, 1, 1, 0, and 1, 1. Then you have, for the output, you have 0, 1, 0.
All right, so we remember this 0, 1. So if we have like A and B, this is A, whoops. This is A XOR B. So that's one way to think of it. Another way to think of it is, well, you can have XOR with as many inputs as you want, as long as it's binary. An easier way to think of XOR is essentially we'll add all of the digits together and then tell you if the result was even or odd. So if it is a 1, it means it was odd. If it's a 0, it means it was even. So especially if we have way more inputs, that's probably an easier way to think about it. So if we had something like this, if we had A1, A2, A3, and let's just assume a single bit, but if it was a byte, you just do this for every bit. Say we have something like this, where A1 is 1, A2 is 0, and A3 is 1. Well, we compute a parity, and our parity is going to be an XOR of all of them. Why did I write the symbol twice? So if you take my shortcut, the parity should be I can add all them together and it will tell me whether or not the result was even or odd. So 1 plus 0 plus 1, is that even or odd? Even, so what should the result be of XORing all of them? 0, right? So now this is a nice trick. So knowing that, well, if for some reason, say A2 is dead. So A2 has now just lost data, and that disk is dead, and now I have no idea what this is. So can I work backwards using this and knowing the value of A1 and A3 to get me what this should be, if it should be a 1 or a 0? Yeah. So in this case, well, my parity tells me that if I add everything together, it should be even, right? That's basically what that says. So the two values I have that still exist are 1 and 1, which are even, which means this can't be a 1. If this was a 1, that would, if I XOR all them right now, then that's odd, which conflicts with the parity I calculated, right? So that means that if this can't be a 1, it has to be a 0. So I can reconstruct it. I can get back to the original value knowing that parity information, right? And this works no matter what dies. So if I have something like this, and then I lose A1, then knowing that A2 was 0 and A3 was 1, and if I add everything together, it was even, well, that means A1 must have been a 1, so I can reconstruct it, right? So any questions about that? Yeah?
What if 2 disks die?
Sorry?
What if 2 disks die?
Yeah, what if 2 disks die? So if it's like this, what can you do?
You can get the 2 values, but it will be like, they're in the right place.
Yeah, so in this case, both of those are valid solutions, right? And one's right and one's wrong. So if 2 disks dies, you're screwed. Yeah.
I mean, wait, I'm just curious, but like, if you had 2 different parity disks where one didn't XOR between, or never mind actually, because I was thinking if 2 disks die, you have an XOR between the 2 disks and store that into a different parity, but that would be really wasteful.
Yeah, so we'll get to that. Well, the second, if you wanted to protect against 2 disk failures, it gets much more complicated. It gets to like math stuff. Yeah.
So is this concept like applied to all the different bits in each disk, or?
Yeah. Yeah, so this is just showing a single bit on a disk, but if those A1s were bytes, you just do the same thing. It's just the same XOR across all of them. But the concept's the same thing. It's just deal with every single bit. Yeah.
So like when a disk dies or like a bit in the disk dies, is it died because you might have deleted it or you might have erased it, or is it just died for any random?
No, in this case, we're assuming disk failure, like the entire disk is dead. Yeah, just died. So in this case, yeah, that means the entire disk is dead. So we can recover. So through that, we just argued that we can recover if a single disk dies, right? One disk dies, we're good. What about performance? So is yeah?
Like reading and writing should be twice as fast because you have 3 disks you're splitting up the.
Yeah, so in this case, reading and writing is about 3 times as fast because minus that one disk, it's the same as RAID 0, right? So I'm essentially just using a single disk for parity, and then that's it.
But it wouldn't be exactly 3 times because you had to calculate parity.
Yeah, so that's right. So it wouldn't be exactly 3 times because we're going to waste some time calculating the parity. So we'll have to calculate it and then also write to this disk. So for this, also in this case, if all those drives are 2 terabytes, then suddenly we can use 6 terabytes of usable storage, right? Because one disk is set aside for parity, and then we're essentially striping data across the remaining 3, so we can use all the information minus the one disk. Yep.
For the parity, do you have like hardware to do it instead of just like soft logic?
Yeah, so you can, some things do it in software, some things do it in hardware. Most things do it in software now. You can see that this is kind of a bad idea, and because say on disk 0, we change A1, and on disk 1, we change B2, and then on disk 3, we change C3. Well, guess what? This disk will get hit by every parity calculation. We'll have to write 3 times, while each disk is only writing one little circle there. So we create kind of a bottleneck with that parity disk too, which isn't great. Yeah.
If the parity is calculated on like using soft logic, won't that take a lot more time because the memory has to reach the CPU and then the CPU will calculate the parity value and then it'll go back to the disk?
Yeah, disks are way slower though than the CPU. Like disks are many orders of time slower.
Even if you were to use like, an external digital circuit that XORs all the bits?
But for that, the operating system is telling what disk to write anyways. So that's going to be in memory, so it can just XOR it. Yeah.
How many disks does a typical hard drive usually have, I guess, then?
So each one of these disks is a separate hard drive.
Okay.
So this would be like you go to the store, you buy 4 disks. These are all physical different disks. So this is only for when you care about your data, because in most of our computers and any of our laptops, it's a single disk, right? So we're kind of screwed. But if you actually care about your data, use something like this. So in this case, well, we get to use essentially all of our available space minus one disk because we're using it for parity, and this technique requires at least 3 drives. The pro is essentially we get n minus 1 times performance. So if we had 5 disks, for example, well, one of those disks is for parity and the other 4 are for striping. So yeah, we basically get n minus 1 times performance. And if any disk fails, we can recover. We can just throw it on there, recalculate the value it should have had, and we're good to go. So the con is that write performance can suffer because of everything being bottlenecked on that single parity disk. So even everything needs to change on that disk. Yep.
Just a question about RAID 1.
Mm-hmm.
So if RAID 4 has an n minus 1 performance, does that mean RAID 1 has an n over 2 performance?
So it's like just n times more performance.
N times more performance than RAID 1?
So it's always compared to a single disk. So RAID 1 the read performance, if I have 2 disks, it'll be 2 times faster than a single disk. If I have 3 disks, the read performance will be 3 times faster than a single disk. For write performance, it's the same as a single disk, right? In this one.
Why is it? Wouldn't it be 2 times slower because you have to write to both disks?
So you can assume you can write in parallel. So yeah, we're assuming we can write in parallel. So it'd be the same as a single disk. So any of the comparisons are always in relation to a single disk. So here when we say n minus 1, so that's the number of times. So in this case, we have 4 disks, one's using for parity, so it's 3 times faster than a single disk. All right, so now to get to the fun one. So we can actually fix this con. So we're kind of bottlenecked on the parity disk, and now we get into the first RAID level that is actually used. Well, RAID 1 and RAID 0 are used, but RAID 5 is the first one with some parity that's actually used. So the only change here, conceptually, it's exactly the same as RAID 4, except we just distribute the parity blocks across all of the disks. So instead of disk 3 having all the parities, well, disk 3 has the parity for A, and then in disk 2 it has the parity for B, and disk 1 has the parity for C, and then disk 0 has the parity for D. So it's otherwise exactly the same. We just take that parity information, distribute it across the disks. So nothing else really changes except we remove that bottleneck, right? So any questions about this? Yeah.
How do you indicate that where the parity lies? How does it know where the parity?
So the kernel would be keeping track of which block is the parity one, right? So that'd be part of the kernel, part of the file system for that. So this, again, remember 1 disk failure and we're good, 2 and we're not. So this is what I had when I was working on my thesis. A disk drive died and I was okay. So I continued working on it thinking nothing bad would happen. But disks usually die quite close to each other. So before I got to replacing the disk, guess what? Another disk drive died. And what happened to my work? Yeah. So don't be me. If you do something like this and the disk drive dies, go replace it. And don't be me. Yeah.
I never experienced this dying. Like, what causes that?
So especially for magnetic disks, they don't last that long, like years or something like that. So if you tried to buy like, a 12 terabyte SSD, that's going to be like thousands of dollars. It's going to be pretty expensive. But if you buy one of those magnetic disks, it's like $300, $200, something like that. So it's a lot more affordable. So if you're storing, like I back up all my lecture files on my recordings, which are gigantic, so they're on like a RAID 5 drive because I can't afford a RAID of SSD drives. I don't get paid that much. Yep.
So you have, if you wanted to implement RAID 5 or RAID 4 drives, you would have to buy them. Could you implement them yourself, using multiple drives and connect them together?
Yeah, you could implement them yourself, but typically people just on Linux or whatever, you just set up, there's like a RAID file system, and then you set that up, and then you can put anything else you want on top of them, and then the kernel will just take care of doing all the RAID stuff.
So you don't have to buy a single RAID 5 or a singular package RAID 5?
No, you just buy a bunch of drives. They just should all be the same size and be similar characteristics because you're limited by the slowest one anyways. So you pretty much just always buy them and they're always identical. And then if you want to upgrade, you buy another 4 ones that are identical and just replace it. Unless you're Google, and then you buy like hundreds of these damn things. So
Just save in the cloud, I guess.
yeah, well, this is saved in the cloud, so this is what the cloud uses. So if you do the cloud, what's the quote? The cloud is just someone else's computer. So nice thing about that is if a cloud drive dies, some guy in a data center is going to go replace it for you. You don't have to go to the store or anything. It's basically like insurance. And they get to fix it, right? They get to rebuild it and all that fun stuff. So This is what you were talking about. Hey, let's add another parity calculation so two drives can die. So that's exactly what RAID 6 is. So RAID 6 adds another parity calculation. So this P would just be an XOR, and this Q would be a new parity calculation such that if any two die, I can recalculate. You might ask, what is that parity calculation? And I will refer you to the CS department, because that gets into like some heavy math. If you've never heard the term Galois field, then you will not understand it, and I do not understand it. So you have to take like some grad math course to understand what it does. Just know that it is possible, and some math geek has figured it out. So with this, we have extra parity. So we're essentially using two disks for parity. So two disks can die and we don't lose any data, but now we are using another disk for parity, so we have less available space. So for this, we need at least 4 drives, so 2 for parity and 2 working, and we have way less available space. So in this case, if I have 5 disks and they are all 2 terabytes, well, if I'm using RAID 6, I can only use 6 terabytes of storage because 2 of them are used for parity calculations. So there's always a trade-off. I have less usable space, but I can survive 2 disk failures now. And if I had RAID 5, well, I have more usable space, but I can only survive 1 disk failure. So it depends on what your level of tolerance is and how much you care about your data. So I probably should have cared about my data a bit more. But again, I could only afford 4 disks, and I didn't want to half the speed, so yeah. So write performance is going to be pretty similar to RAID 5, but it's going to be a bit slower because now I have to do 2 parity calculations instead of 1 and write a bunch more information. But we can just say it's about the same. It'll be a bit slower, but not significantly. Yep.
So when you use RAID 5 and RAID 6, is it like a lot slower that you'll recognize it if you were used to SSD speeds?
For spinning disks? Depends on the solid state drive because some of them are way faster than other ones. So
it's like a cheap one, not an NVIDIA, like a really top of the line NVIDIA.
Cheap one, if you have enough drives, you won't really notice that much. These drives, standard hard disk drives are like 120 megabytes a second. Some crappier SSDs top out like 800-ish, something like that. I forget something like that. So as long as you have, what, like 6 of them, it's about the same. So it takes a while. And if you've seen some big data hoarders, their server will have like 48 drives or 50 drives in them. So at that point, performance is pretty much faster than an SSD anyways, but they also spent thousands of dollars on it. So any other questions for fun RAID stuff? How many more RAIDs are there? So the other one that is sometimes used is something called, so there's RAID 0 and RAID 1. Some people combine these in something called RAID 10 or RAID 1 plus 0 or whatever, where they will essentially do the striping like this. So there'll be a RAID 0 where you don't have any extra copies of anything. And then they'll do a RAID 1 on top of this. So they might have 2 copies of this. So you would have 4 disks, and on 2 disks, it would look like this. One would have half the data, the other would have the other half. And then there would be another 2 disks that are a copy of these. So you essentially would have 4 disks. One has one, or 2 would have one half, and then 2 would have the other half. So you can see with that, here. So with that, you would get slightly more or less lucky. Actually, change the color. So if I had RAID 1 plus 0, it might look like something like I have disk 0 with A1, disk 1 with A2, and then here I have my, my level 1, and between these disks would be like a RAID 0, and then we have a RAID 1 on top of that. So these extra disks would be new copies. So this would have A1, this would have A2. So now, how many disks could fail before I lose data? 2. So yeah, I could lose this one, and then this one, and then I now lost data. But I could get lucky, right? If I, what about that? Have I lost data in that case? No, so 2, I could survive 2 if I got lucky. If the wrong 2 die, I get unlucky. And that's the same thing if I extend this even more. So say I added another pair. And I had disk 4 and disk 5. And I had, A1, A2. So how many disks could I withstand losing now before I lost data? 3, right? It depends how unlucky I get. So if I lose this disk and this disk and this disk, well, I've lost some data. But I could, if I got lucky, I could lose all of these. I could lose 4, and I'd still be fine. You're essentially going up to the gods. So you have like a variable level of tolerance depending on how lucky you get. So this is like a good spin the roulette wheel. But in this case, I'm essentially just wasting half my storage. Yeah, and I could also split it up. So instead of doing this, I could also split it up that I only have 1 mirror of RAID 0, so this is more typical. And if I added another 2 disks, I would instead, okay, can we stop? So that one's a bit more wasteful because, well, I waste like 1/3 of my data. I ideally would just like to waste half of it. So you do something like this. Disk 2, disk 3, disk 4, disk 5. So now how many disks can I lose before I have some failure? No, A3 is just data. There's no parity in this. So if I got unlucky, 2 and I'm done, right? Well, if I got super lucky? Yeah, if I got super lucky, 3. So same idea here. But in this case, well, each of them are different, so I can use half of my space, right? So I essentially just have 1 RAID 0. I just have 1 copy of everything. Yeah.
Do they ever use like if you have like a RAID 5 and then you duplicate it so you do like a RAID 10, I guess, on it?
So RAID 10s are only like just mirror and striping. You don't really do it. You don't really mirror a RAID 5. It gets kind of messy when you do that. But like some people, if they have, the disks of, or like the drawers of 45 drives, like they'll RAID 5, like 6 of them, and do multiple RAID 5. So RAID 5 another 6, RAID 5 another 6, RAID 5 another 6, and then kind of combine them all together. So it looks like one big hard drive. So you can withstand more failures. So that again goes to like your level of tolerance of how many drives you want to fail. But if you have like 40, yeah, if you had 40 drives and you just did a RAID 5, if 1 of 40 or 2 of 40 drives die, you are screwed. So you probably don't want that. So you can break it up into smaller RAID 5s if you want. That's typically what happens. Yeah. So industry, again, it just depends, right? So there's more complex file systems that will let you combine stuff for like so more complicated things will also have disks on multiple servers and then have redundancy between servers. So like, I don't know, like S3 and stuff like that, or Google's distributed file system, that will make sure that there are like 3 copies of the data across the world. So there's a whole bunch of trade-offs. It just depends on your tolerances. Yeah.
So if you use RAID, does your file explorer look the exact same?
Yep. Yeah, if you use RAID, your file explorer looks the exact same. The low-level details the kernel gets to handle, but it just looks like, to you, it just looks like the same file system, right? You can upload your file to the cloud. It could use some crazy distributed system, like your file, if you upload to the cloud, it'll be on a hard drive somewhere, right? It's not going to be on a single hard drive. It's going to be, pieces of it are going to be all over the place.
Well, it literally looks like one hard drive.
Yeah, but it still looks like one hard drive, right? As far as you're concerned, the cloud has a copy of your file. Looks the same. But that's part of the illusion of all the software, right? It wants you to think that there's one file because that's easy for you to understand. You're not going to understand. If they told you every time, like, some drive that was holding your data failed, you would probably freak out and go crazy because it probably happens more often than you think. But yeah, that's why they guarantee. That's why, like, if you look at the cloud provider thing, they won't guarantee 100% of the time because they could get super unlucky, whole bunch of drives die, and then you lose your data. That's why it's like 99.999999999% because you could still get super unlucky and lose some data. Yeah, if you look at the history of, like, I don't know, Reddit outages or any big Netflix outages, stuff like that, that can happen. So even if you have a big distributed thing, well, they live in a big data center. So if you have 3 copies across 3 different computers, then most of the time you're good if a computer dies. But if the entire data center goes down, then what can you do? And then, oh, now we have to back up things across data centers, and then if the unlikely event of 2 data centers die, then, right? So yeah, but that's more in line with, like, the distributed computing course that comes after this, which is why this is a prereq. So any other questions before we wrap up? Yeah.
So like, I'm just wondering, is RAID, like, so RAID is like very user-friendly for someone who's not like very, very advanced in distributed system. Are there other like user-friendly distributed systems out there that are very common, I guess?
So it's not real. So distributed system usually means between 2 computers. This is just within a single computer. So it's not really a distributed system. So, but like, I mean, the most common distributed system that's everyone uses is just the cloud. Because that's all distributed, but you have no idea, right? But famous quote, cloud's just someone else's computer. But it'll do this stuff. All right, any other last questions? All right, let us wrap it up and go for reading week. Hell yeah. All right, so this are the things that enable persistence. We explored 2 topics, SSDs and RAID. SSDs, more like RAM, so it has some random access. It's divided into pages and blocks, which is pretty annoying because you can only erase blocks at a time and you can only write a page to a freshly erased page, which gets really annoying. So your operating system's going to have to do some clever things and work with the SSD to get the best performance. One of those things is called trim, which is just letting the SSD know that you are not using any pages on the block, so it can just freely erase the block and allow you to have some fresh pages. Then we saw RAID. RAID is a fun topic. Gives you lots of opportunities to tolerate failures and improve performance using multiple disks. And as we saw today, there's like RAID 0, RAID 1, RAID 5, RAID 6 that all have different trade-offs in terms of how many disks can die in order for you to still retain data. And you can also combine them like RAID 1 plus 0. So remember, pulling for you, we're on this together, and happy reading week.